Okay, now that you all are experts in writing and naming compounds, we need to take a look at how these molecules are actually arranged in space. One thing that you do need to keep in mind is that molecular structures are in three-dimensional space. Okay, so it's not 2D, it's 3D. So in order to take your notes, you need to set up a table just like the one I have here, showing your electron regions, how many lone pair of electrons, how many bonded pair of electrons, the Lewis structure, what is the bond angle, the actual molecular geometry, and then what is the name of that molecular geometry. You're going to be responsible for predicting the molecular geometry by the electron regions in the molecule. So the example I have here is water, which has 4 electron regions. It consists of 2 lone pair of electrons. And you can see that through the Lewis structure right here. So you have 2 lone pair electrons, and then you have 2 bonded pair of electrons. This is the bond angle that you'll get as you go through this presentation, and then also how to predict the molecular geometry and what is the name of each one of those. And so make sure that you create a table in your notebook and record all your information, because you're going to be responsible for knowing this. All right. So what is molecular geometry? I think it's pretty straightforward. It's the arrangement of atoms within a molecule. A molecule can consist of non-bonded electrons, which we generally refer to those as lone pair electrons, single bonds, double bonds, and triple bonds. Each one of those would be considered an electron region. So if you have a double bond, that would be just one electron region, or domains. But for the purpose of our presentation, we're just going to refer to them as electron regions throughout the presentation. All right, so this is very important that you understand what consists of an electron region, and that is a great test question, hint, hint. And so make sure that you're able to identify each one of those. Okay, so here, excuse my drawing. I'm still working on getting the hang of my tablet for straight draw. And it's a little, well, could use some work. Whoops. Okay, so this is a water molecule. Again, here's your lone pairs. These are the bonded pairs, usually demonstrated by a straight line. You have 4 electron regions, 2 of them being the lone pair electrons and 2 bonded pair of electrons. We can't really predict the molecular structure off of the Lewis dot, because as you can see here, there's a couple different ways that you could actually write the Lewis dot structure. You could have it where you have this kind of upside down L shape, or where they are side by side. So that doesn't really tell us what the molecular structure is, and so it just gives us the Lewis dot. There's some things that we have to know about the behavior of molecules in order to actually predict that. What we use to predict the molecular structure is called the valence shell electron pair repulsion theory, or VSEPR. VSEPR is used to predict the molecular geometry of a molecule, and what it is the tendency of a lone pair of electrons and the bonded pair of electrons around a central atom to repel and move as far apart from each other as possible. Okay, so remember, electrons are all negative, and we don't like each other, so we want to get as far apart away from each other as possible. And so that's what governs a molecule's orientation, is that they try to situate themselves to where those electrons are as far apart as possible. Okay? And so this is very important to understand what that VSEPR theory means. So first of all, we're going to look at molecules that only have bonded electrons, bonded pair electrons. They don't have any lone pairs whatsoever. We'll go through these, and then we'll add in those lone pair electrons. All right, so we're going to look at these individually. The first one we're going to take a look at is linear. Now, one thing I do want to state up front is that the molecular geometries that you guys are looking at are only a few of the many different orientations that are there, but that really does exceed this class, and if you go on and take additional chemistry courses, you will get a more in-depth of the different molecular shapes of different molecules. But for our purposes, we're going to stick with the top most common molecular structures. So the first one we're going to look at is linear. When we have a molecule that consists of just 2 electron regions, there are no lone pair electrons, they're all bonded. What happens is, and then also remember, and we've talked about this before, is that when we talk about lone pair electrons bonded, that is to the central atom. Okay, I know that we have some unbonded lone pair electrons here, but these do not matter when we talk about the molecular geometry. It is strictly what is around that central element. Okay, so in this case, we have 2 electron regions. We have a double bond here and a double bond here. Okay, and so that's 2 electron regions which only consist of bonded pair. And in order for these to get as far apart from each other as possible, they take on a linear 180-degree angle from each other. All right, so you could even play with that, move these molecules around, and what you're going to find is the greatest distance between them is that 180-degree angle, which is your linear. You see this right here, this MX2, and what that is, it's just a kind of generic formula. The M stands for, it's just a symbol for the representing the central element, and then this X here, the X is your peripheral atoms, which are the ones that are attached to the central atom. Okay, so you have 1 central element, and then you have 2 peripheral, which are your oxygens. And so that's just a generic representation for that. So what do you need to know for this? Linear. 2 electron regions, 2 bonded pairs of electrons, no lone pair electrons, creates a bond angle of 180 degrees. There's your structure, there's your Lewis dot, and it is called linear. Okay? The next one is when we have 3 bonded pairs of electrons. No lone pairs of electrons. Remember, we're only focusing on molecular geometry that has bonded pairs with no lone pairs. All right, so you have 3 electron regions. You can see them here between the boron and the fluorine. And then again, this generic representation is you have a central element, which is your boron. It has 3 peripheral atoms, which is your fluorine, and so that's just that generic representation. So in order for these to get as far away from each other as possible, they form a bond angle of 120 degrees. So you can see right here. So they're all equally spaced. You have 120 degrees here, whoops, excuse me, 120 degrees here, and 120 degrees here. That all adds up to 360. You're in the one plane, forms the shape of a triangle, so trigonal planar. Okay, is the linear structure, not linear structure, is the molecular structure for an atom that has 3 bonded pair of electrons with no lone pair. That's trigonal planar. All right, so moving on up, now you have 4 bonded pair of electrons with no lone pairs. These form a tetrahedral. Tetra meaning 4. And you can see here you have 4 electron regions, and that's that carbon to hydrogen bonds. Generic representation, generic representation, this MX4, central element, 4 peripheral elements. Forms a bond angle of 109.5, giving you, that is the space in between these bonds to get them as far apart away as possible. If you can't look at this one like we did the last one where we took all the bond angles, added up, and got 360. And the reason this is, remember, we're in 3D, and what's happening is in the 3D space, it's not just in one plane. You can see this hydrogen in the back here, it's pushed down like a pyramid on the bottom. So this bonded pair of electrons, in order for these to be as far apart from each other, it pushes it down to where you really do have more of a pyramid structure on the bottom. And so those bond angles here would be 109.5. So for here, what you need to know, four electron regions, for a bonded pair of electrons, no lone pair, forms the tetrahedral, bond angle of 109.5. Here's your Lewis dot. Here's your molecular structure. Okay, so those are the ones that we're going to focus on for having no lone pairs. They just have bonded pairs. But then what happens when we start adding in lone pairs? Because we know we have a lot of molecules that have lone pairs of electrons. So how does that affect the molecule differently than when it has a bonded pair? And this is key. Lone pair electrons need more space than bonded electrons and will bend or compress the angles between the bonded electron pairs. Okay, so they cause a slight variation in the bond angles because they need more space, so they force those bonded pairs down. And the first one we're going to look at here is called a bent. All right, so you remember from the last one we did this, it was they used the MX symbols. Well, here this is the exact same thing. A is your central element, B is your peripheral atoms attached to it, and then E is the number of lone pair electrons. So in this one for bent, there are different variations of bent, but for this one is you have your central element, 2 peripheral atoms, and it has 1 lone pair of electrons. Same thing what we're saying here. Okay? This is an additional piece that we look at when we have lone pair electrons, is that when we actually draw out the Lewis dot structure and arrange them, you get a trigonal planar type orientation. But because these lone pair of electrons have a different effect than if this was bonded to an atom, it changes the shape. You don't have an additional element up on top here. You don't have another, in this case it would be you're represented with a B. And so that does cause some variation in the shape. So here what happens is you have these lone pair of electrons up top, and it forces these bonds downward. Okay, so this needs a lot more room. They're really negative. They're not bonded to anything to kind of distribute out that negative, and so it forces them down. The example here is SO2. You have a sulfur with 2 oxygens bonded to it. That leaves you, if you worked out the Lewis dot, that leaves you with 1 pair, one lone pair of electrons, and that gives you a bent orientation. Okay? The second one is also a bent orientation, but it has 2 lone pairs of electrons. And I may have to go back. Oh, okay. So on this one here, I'm going to just skip back for just a second, is the bond angle that's formed here between these 2 bonded pair of electrons is a 120-degree angle. You'll need that for your sheet. So between these 2 oxygen bonded pairs, bonded to the sulfur, that is a 120-degree angle. All right, so we have a second bent. Well, this is in the case when we have 2 lone pairs of electrons. All right, so here's your symbol right here, is you have central, 2 peripheral atoms, but you have 2 lone pair electrons. Same thing what we said here. That gives you a total of 4. 2 lone pair, 2 bonded pair. If we draw out the Lewis type structure for it, it would really give you a more tetrahedral kind of look. But again, remember, they have these lone pair of electrons have a different effect on the molecule orientation or the molecule geometry than those bonded pair. So it bends it down even more so than if you only had 1 lone pair. Because remember, they need a lot of room. the example of water, the water molecule. And what you're going to see here is that this is going to create a bond angle between these two bonded pairs of electrons of 104.5 for a water molecule. Now, just a note, typically everything but water, and again, remember, we're dealing with chemistry here. We can predict as best we can. We can group them as best we can, but at the end of the day, this is nature, and it puts things together. There are some additional factors with a water molecule that we'll talk about when we get to discussing that part of chemistry. But typically, a bent or molecular geometry with two lone pair of electrons would give you a bond angle of 109.5. Water's a little special, giving you, and it comes in at about 104.5. It changes up the angle slightly, but typically this type of orientation with any other molecule would be 109.5. Okay, and so our last one that we're going to look at is called a trigonal pyramidal. Okay, so you see the word pyramidal in there, you see trigonal, so that obviously you're going to have a formation that includes something that's going to look like a pyramid and something that's going to look like a triangle. And so if we look at it here, again, same representation, central element, 3 peripheral, 1 lone pair of electrons. Total for 4 electron regions. Remember, 3 of them being bonded, 1 of them being lone pair. If you were to draw it out, it would give you a tetrahedral kind of electron geometry. But again, lone pairs change the orientation. And so what happens is, remember, it's 3-dimensional. And so these lone pair of electrons push down, let me see here if I get my mouse back. Oh, here we go. Push down these bonded pair, creating this pyramid type structure. So think about if you had this molecule in front of you, we'll make them in class, is it forms more of a pyramid on the bottom, and each one of these pyramids, if you can see here, has a triangle configuration. Trigonal pyramidal is where it gets its name. And so typically one of the best examples we use for this is NH3 or ammonia, where we know that ammonia has those 5 valence electrons. It will have one lone pair, and then it has 3 open bonding places where it can bond those 3 hydrogens. All right, those lone pair of electrons, again, they need more space, so they're going to push those down, and they change up that bond angle. So for trigonal pyramidal, your bond angle is going to be at 107. Okay, this looks very similar if you go back and look at right here. So if we looked at the tetrahedral bond angle was 109 degrees, so 109.5 degrees. So the only change between the tetrahedral, the CH4, which you had 4 bonded pair of electrons, and this one with 3 bonded pair, 1 lone pair, is that because it is a lone pair of electrons, it does change that bond angle because, remember, those lone pairs need more space. It forces it down and giving you 107.5 bond angle. So it changes it by 2 degrees. Okay, so those are things to really keep in mind. That's a great test question, is for me to ask you what's changing the bond angle on these ones as you change the number of lone pair of electrons. And the simple answer to that is that the lone pairs of electrons need more space, so they push those down. All right, so to wrap it up, make sure that you understand that lone pairs of electrons need more space and cause a bending of the bonded pair, changing the bond angle. You'll be responsible for identifying and drawing linear, trigonal planar, tetrahedral, bent, and trigonal pyramidal. And in addition, you'll have to identify the number of electron regions of that molecule. All right. Again, feel free to go back and watch the video for close any gaps of any understanding that you have, and then be prepared to work on activities and create these molecules in the classroom.